Okay, let's go then. All right, so this is slightly intimidating. Here I am, an Englishman who lives in New York City, talking about the Southern Plains to people in the Southern Plains, but be gentle with me. So this is some work we did with a couple of summer undergraduate interns, Nathan Liss and Jamie Feldman, a couple of years ago. And the first thing that got me interested in this was when at a faculty meeting, someone who runs an organization here that makes population maps of the world gave us these little cloths. It's that like kind of cloth that you use to clean your spectacles or your computer screen. And I looked at that and I saw that, you know, there are two straight lines on that map. One is south of the Sahara in the Sahel. This is population density. Well, we know why that's there, but then the other one is around about in the center of the plains, going north-south, around about at the 100th Meridian, where apparently there's a very dramatic drop-off in population density that occurs there. And I looked at that and thought, wow, is that real? That's really, really striking. And why is it that there is such a strong divide there in just the number of people who are living there? So we were, of course, quite familiar about the idea of the 100th Meridian and how it is a divide between the arid west and the more humid east. And we've spent years working on hydroclimate, drought problems in Western North America. So this was like, of course, not news to us that there is such a divide. The concept of that divide being there goes back to John Wesley Powell, who did tremendous amount of work for the US government with the Geological Survey and the Bureau of Ethnology in the West. And the message that he was getting across was that settlement of the West was going to have to be very different to settlement of the East because of the much more restricted water supply over in the West. And he put that in this report on the lands of the arid regions. And that wasn't really very welcome by politicians at the time. The idea that there could be environmental limits on development were not very welcome to those who were attempting to develop the West and hoping to greatly develop political and economic power over there. And the idea that there are limitations over there has lived on in resentment for quite a while. This, I think, is a road sign from North Dakota, where it goes on complaining about some geographer who labeled it the east edge of the Great American Desert. Implies that the geographer had never been there, but of course he had been there plenty. This road sign claims that the 100th Meridian is just another bad memory, but it, you know, as you can see in that population map I showed you, the fact that there is this arid-humid divide has in the end had quite a big effect on the way the American land use, the American economy has developed. So Powell had some ideas about this that he put in this article that was in Century Magazine. That's a building in Greenwich Village where Century Magazine was published. Quite familiar to me because it's where Astor Place Wine and Liquor is, in the basement there, the best wine store in New York City. After some language describing the transition across the 100th Meridian, he came up with an idea, which I'll read. The winds in their grand system of circulation from west to east climb the western slope of the Rocky Mountains, and as they rise, they are relieved of pressure and lose their specific heat, and at the same time discharge their moisture, and so the mountains are covered with snow. The winds thus dried roll down the eastern slope into lower altitudes when the pressure increases and they are heated again, but now they are dry. Thus it is that hot, dry winds come now and then and here and there to devastate the subhumid lands, searing the vegetation and parching the soil. So he obviously was thinking of two mechanisms here. One was a fairly familiar rain shadow effect. The other one was related to the adiabatic warming of the land as it descends the mountains, and was implying that great aridity of the atmosphere extracted moisture from the soil. So there's two mechanisms that he was considering. Powell, of course, is famous for this plan in this beautiful map he made of how he thought the West should be settled, which was based around watersheds and multiple use depending on altitude within the watersheds, and a lot of self-organization by the communities out there. It wasn't proposing a government plan. Regardless, this plan really wasn't followed at all, and the West developed in a very different way to how Powell intended. Later on, around about 1931, Walter Prescott Webb, in his great book, The Great Plains, actually preferred the 98th meridian. He didn't really mention Powell at all, but he made the point that this was quite some decades after much of the West had been settled, that he had already noticed that the settlement was very different. He talked about the ways of travel, so you can look at the railway networks, even weapons, which is an interesting the development of the Colt rifle, Colt repeating revolver, and agricultural methods, plows, and even laws like water law. Everything got modified to the West relative to the East. So what we're going to talk about here is the 100th meridian. Is it real? How is it expressed in terms of climate? Why is it there? How is it expressed in terms of hydrology, vegetation, what would grow there, what currently is growing there, and then in terms of development and farm economy, and then look a bit into the future, thinking about how this divide will change and what the implications might be for the farm economy. So the measure of aridity that we're going to use is the very familiar one, which is the ratio of precipitation to potential evapotranspiration. So anywhere greater than 1, precipitation can meet the demands for moisture from the atmosphere. And if it's less than 1, there's going to be some amount of water deficit. The potential evapotranspiration is computed using the Penman-Monteith method. And it increases with both vapor pressure deficit, the aridity of the atmosphere, that is, temperature, and wind speed. And for data, we're using NL-2 land surface hydrology model. To look at moisture transport in the atmosphere, we'll use the ECMWF ERA interim reanalysis. And then land fire environmental site potential, actual land cover data from the National Land Cover Database. And then for the agricultural work, there's data from agricultural censuses and rangeland data, both from USDA. So here are maps of precipitation, potential evapotranspiration, and the aridity index, and they go by season from fall, winter, spring, summer. And what you can see here is that this aridity gradient in the center of the plains doesn't arise from any one process or within any one season. It clearly has to arise from a combination of phenomena that are occurring throughout the year. If we look at precipitation, we do see that very clear band of low precipitation that's in the plains. The precipitation that comes in from the Pacific is wrung out of the air by the mountains, so the plains are shielded from that. But then the eastern plains and the southeast US get extensive amounts of moisture delivery that comes in from the Atlantic Ocean. So it goes over to less arid conditions over towards the east. In terms of temperature and how it affects potential evapotranspiration, you see how high temperatures greatly drive up the PET in spring and summer in the south to central western plains. So here is looking at it in the annual mean. Now Powell, as I said, proposed 2 arguments, and with this aridity index, we can actually change the way we compute that by removing, first of all, the zonal variations in precipitation. Then we can find out what the aridity index would look like purely due to spatial variations in the vapor pressure deficit. And then on the right, we can remove the longitudinal variations in anything that influences the vapor pressure deficit and look to see what would happen if only precipitation was varying with longitude. And you see that the precipitation is the process that really does strongly creating an arid-humid divide that runs north-south at about the 100th meridian, or it could be the 98th. Whereas the vapor pressure deficit argument that Powell also interestingly invoked does play a strong role in increasing aridity in the southwestern parts of the plains and the southwest more generally. So both are important, but precipitation appears to be the dominant mechanism. So how is that occurring? Here is data from ECMWF. The color is the precipitation. Red obviously means dry, and blue, green, wet, blue, very wet. And we've got it by season again and the annual mean. The vectors here are the moisture transport, and these are computed with 6 hourly data, so they include both the mean flow and the transient eddies. So in winter, the Rockies shield very well the plains from the Pacific storm track, while the Atlantic storm track moves moisture into the eastern plains. So that's quite capable of creating an aridity gradient across the plains. Then in the summer, the whole region is receiving air that's coming in from the Gulf of Mexico. However, the moisture transport within that intensifies strongly from the west to the east. So the western part of the plains in the summer are getting southerly flow, but it's coming in with a southwesterly component, whereas the eastern plains are receiving inflow of much more moist air more directly from the Gulf of Mexico. So even within the southerly flow we have over the plains in the summer, that is capable of creating a west to east precipitation gradient as well. So both winter and summer contribute to make the annual mean aridity index variation that we see setting up somewhere in the middle of the plains this stark arid-humid divide. The southerly inflow from the plains is interesting. It's obviously related to a coupling between monsoons and subtropical anticyclones, with the heating placed over the continents and that will drive southerly flow and ascent by vorticity and thermodynamic balance. But also the blocking of trade winds by the Rockies, creating a northward deflection. And the pictures on the right here are simulations with a GFDL model by Zhang et al., where they have their regular model in the middle, observations in the top, and when they remove mountains, you can see that you only have a much weaker flow into the plains in the summer. So this topographic banding, almost sort of looking a bit like a western boundary current, is part of what sets up this flow. But then there's complex interactions between heating over sloping terrain and other things that go into creating the low-level jet and precipitation that goes along with it. Okay, so moving on from the climate dynamics to looking at how the aridity gradient is expressed in the land surface. Here's this 1 meter deep soil moisture. And again, you can see that this has quite a bit of spatial variation due to river valleys and all sorts of different types of soils and so on. But again, you see that the aridity gradient does get reflected in the amount of moisture in the soil. So we see it there in the soil hydrology. And then looking at what would grow in the plains if it wasn't for human interference. This is from potential evaporation from the land fire data set. And you can see that the tallgrass prairie tends to be over to the east of the 100th meridian, whereas the shortgrass prairie tends to be over to the west. Within between, we have this mixed grass. And so as you go from the east to the west, you're going to progressively shorter grass prairie, which is what Powell was describing. And now beginning to look into the issue of how humans are using the land. So this is from actual land, what is actually on the land now. And you can see, for example, that developed land. So that's all sorts of things. That would be housing, schools, playing fields and things like that. That, consistent with the population, has a stark drop-off at around about the 98th or 100th meridian in the middle of the plains. Planted pasture, so that's more productive pasture, tends to be over in the more humid east, whereas herbaceous grasses tend to be over west of the meridian. The planted cropland is very heavily influenced by seeing there the corn belt, but again, it is predominantly to the east of the 100th meridian. So now looking at other aspects of the farm economy, if you look at farm size on the top right, you see that as you go from the east across the meridian to the west, the farm size increases, and in the top left, the number of farms decreases. So that's consistent with the land in the west being less productive than in the east, so that to make a going of it, you're going to need a larger amount of land to farm. And then looking at corn and wheat, these are percent of total cropland. You see that the corn is mostly towards the east of the meridian. The one exception there is Nebraska, where there's relatively high aquifer there, which allows extensive irrigation of corn. That's the only place west of the meridian that has a substantial amount of corn. Instead, most of the land over to the west is used for wheat, which can grow in a drier climate, and also for rangeland as well. Little of that to the east of the meridian, and much more of that to the west. So clearly this aridity that we've seen in climate and in the land surface has been reflected in the way that farming varies, and in a way that is reflecting the variation in aridity. So how has it been changing? These are Hofmöller diagrams for the northern plains, the central plains, and the southern plains, and the one on the left is the full aridity index. The one in the middle is just the aridity index you would have purely due to zonal variations in precipitation, and the one due to the zonal variations in potential evapotranspiration. So there is some indication that aridity, lines of equal aridity have been moving eastward over the past several decades. And that is coming about being influenced by potential evapotranspiration increasing. But also there seems to be in the southern plains a tendency to lines of equal aridity moving eastward because of declining precipitation in the southern plains. And then the maps show the change in aridity index for everything, for the influence of precipitation in the middle and the influence of PET below. And you can see the influence of precipitation with the declining precipitation in the southwest. But the rising temperature and potential evapotranspiration increasing is more widespread and actually doing more over in the eastern part of the plains than in the western part of the plains. Now, the change that's occurred in terms of precipitation over the last several decades, we think that is quite strongly influenced by decadal variability in the tropical Pacific Ocean. This is an observation of the decadal difference that has occurred 1998. I'm sorry, it only goes up to 2012. I picked up an old picture here relative to the decades before. And then we've got a simulation of that with a model atmosphere model forced by global observed SSTs, and then on the bottom left, forced only in the tropical Pacific. And you can see that models forced by observed SSTs can reproduce this change in precipitation. And the change in sea surface temperature that has occurred over these past few decades is towards the cold tropics phase of the Pacific decadal oscillation. So it's that development of La Nina-like SSTs and how they persisted over recent decades that drove the atmosphere to create this precipitation anomaly in the southwest there. So we think there's a strong role of decadal variability. In terms of the climate change component, this is some work I did with Marty Hurling a few years ago, trying to tease out the human-induced climate change component. And there we see that there's a very modest reduction in precipitation in the southwest that probably is attributable to rising greenhouse gases, and that's consistent with our expectations for the future. But temperature has risen due to human influence much more widely, and that's led to a decline in soil moisture. So we think there is, even over the past few decades, an emerging signal of human-induced change, but much of what has occurred in terms of precipitation is probably more related to the natural decadal variability. So now let's look out into the future and see what happens to this arid-humid divide. For this, we need climate models, and we used 18 CMIP5 models that provided all the data needed to compute the potential evapotranspiration and the aridity index. And we look out to 2099 using a business as usual scenario and one run per model. First of all, we need to look at how well the CMIP5 models simulate the aridity gradient. But before I get to that, some prior work on how we expect hydroclimate over the US and North America to be changing. Again, by season, winter, spring, summer, fall, we do see this decline in precipitation in the southwest, especially in the spring. And P-E, which is seeing the effect of warming temperatures and how that influences evaporation, has a very widespread reduction there, indicating a drying by the atmosphere, especially in the spring and the summer. So the models, how well do these models simulate this aridity gradient? We're reproducing here results in the top 5 panels from NL-2 land surface model, and then the CMIP5 multi-model mean is below. And you can see that they do a pretty poor job of representing the starkness of this aridity gradient. It's there, but it's much more muted. All of the west is too west in these models, and also these models have too little potential evapotranspiration in the southwest. So the reason for the former problem is that the mountains in these models are not big enough, and that allows Pacific moisture to leak too far east into the plains, reducing the aridity of the western plains. And also these models seem to have excessive moisture cycling, so there's too much evapotranspiration going directly into precipitation. And that would tend to reduce the aridity index as well, compared to the real world, where more of the precipitation is being moved in by the atmosphere and less is being recycled. So we had to perform a bias correction to do this. So we compute fractional changes in the aridity index from the models and then apply them to the NL-2 aridity indexes, so that we maintain the structure of the observed aridity index, but change it, but apply just the change in the models to that. So here it is, the bias corrected aridity index for the next 2 decades, all the way out to the end of the 20th century. And then the raw values are at the top, and then the lower 4 panels show you the change relative to the recent period. So according to this measure, the aridity increases everywhere. It actually increases more in the east than in the west. So this would have an effect of making the gradient weaker, even though aridity would increase on both sides of the gradient. And then we can look to see, well, how much of that is due to the change in precipitation. That's what I'm showing here. And then later on, I'll show how much of it is due to the change in potential evapotranspiration. So here we see that the change in precipitation is primarily increasing the aridity in the southwestern part and in the southern plains, and reducing it up in the northeast. That's not an east-west pattern there at all. It's more of a southwest-northeastern pattern, reflecting the model projected changes in precipitation. But then now we have the part that is just due to the change in potential evapotranspiration, and that's more widespread as warmer temperatures increase atmospheric aridity and extract moisture from from the soils, but it has the effect of increasing aridity more on the east of the meridian than on the west. So again, we can go back to these Hofmollers for the northern, central, and southern plains, and you see these tack on the observed record up to 2015 with the model projections going out to 2099. And you can see this steady march eastward of any lines of equal aridity. So this is what we use to rather sort of colloquially say the 100th meridian moves east. And that movement is more in the southern plains than it is in the northern plains. Okay, so that was due to both a change in precipitation, declining precipitation in the southwestern plains, but elsewhere is largely due to the rise in temperature and PET. So now we can look to see what the implications would be for the farm economy if nothing else changed whatsoever. So here for the north, central, and southern plains, we've replotted the data I showed you before, where we've binned everything by the aridity index where the location is. So we have farm size, percent corn, and rangeland. So there in the northern plains, you can see that as the aridity increases, farm size goes up, the percent of corn goes down, and the percent of rangeland goes up. And you see these relationships are reasonably strong for many of these variables, but for some, like corn in the southern plains and in the central plains, it doesn't work very well. That's in the central plains, that's really because of Nebraska and irrigated corn. And I believe there's some irrigation in Texas as well. But for across the plains, the relationship for farm size and rangeland is quite good. So with those same relationships, we can then use the aridity indexes in the future and see how things evolve. So we have the historical is the blue line, and then the black line is the middle of the century, and the red line is the end of the century. So we see that in the northern plains, we would expect a reduction in the fraction of the land surface being used for corn, and an increase in the land being used for rangeland. In the southern plains, we see quite an increase in farm size and also an increase in rangeland. We did this for wheat as well, and in some places this highly simple model would suggest a replacement of corn with wheat. So I really want to emphasize that this is naive. It obviously holds everything else constant, which it will not be. Farmers will try to adapt to this and so on. However, it does suggest that in the way that how the land is used, the size of farms, what is grown, has reflected the aridity in the past, that's almost certain to some extent that as the aridity changes in the future, it will be reflected in these agricultural practices. However, crops have different values and farmers will be making decisions. Maybe irrigation would come in, maybe they would accept a lower profitability with corn, but still stick to that. And a more complicated calculation really needs to be done to look at this. And the Economic Research Service at the USDA did these calculations a year or two ago. And when you really consider all the aspects of the farm economy, it gets more complicated than this. So just to finish up, I hope I'm on time. Powell was right that this is a very real arid-humid divide. It arises from processes throughout the years. The rain shadow effect of the Rockies and also the location of the Atlantic storm track. And then the way that the southerly flow divides up over the plains in the summer and where that brings moisture to. It's very much expressed in terms of soil moisture and potential vegetation. And then it works through all the way into settlement, crops grown, farm economy. And we were curious actually whether when we started this, whether the physical how the land was used had been influenced by any land policy, like federal policy or anything like that. We couldn't find any evidence of that whatsoever. The 100th Meridian is not encoded in any significant pieces of legislation. So we didn't think that that was the case. We thought instead the human geography must have adjusted to the physical geography over the past century. So climate models predict that this aridity will intensify, the zonal gradient will weaken, but the climatic 100th meridian will advance eastward, and that's both an effect of reducing precipitation in southwest and increased PET everywhere. If nothing else happened, this would lead to a shift from corn to wheat and grazing land and an increase in farm size. But of course, lots of things, technology, markers, the biophysical effects of CO2, which we aren't considering here, could play an influence as well. So that's it, and I would be happy to take some questions.